On January 27, 2023, a tragic incident occurred where a reverend was electrocuted while standing in a baptistry pool during a service. The reverend's death was attributed to a faulty heater in the baptistry pool. The reverend's widow has filed a lawsuit against the contractor who installed the heater. The lawsuit alleges that the heater was damaged because it was turned on while dry, allowing the heating element to leak current into the water. The lawsuit further alleges that the installation of the heater violated multiple electrical codes. To prevent electrical shock in water, all electrical components must be properly grounded. Grounded copper pipe could have carried any stray current to ground, preventing the water from becoming electrified. A ground fault circuit interrupter, or GFCI, is a type of electrical outlet that automatically shuts off power when it detects a ground fault, such as current leaking into the water. If a GFCI had been installed, it could have prevented the electrocution. Regular electrical inspections are crucial to ensure that all electrical systems are safe and meet code requirements. Only trained and qualified electricians should install and maintain electrical equipment. Never operate electrical appliances near water without proper precautions, such as using a GFCI outlet. It is clear that multiple safety violations contributed to the electrocution. Proper installation and maintenance of electrical components, including grounding and GFCIs, are essential to prevent electrical accidents in water settings. Electrical safety in and around water is paramount due to water's conductive properties. Even small amounts of current can be lethal. That's why adherence to electrical codes and the implementation of multiple layers of safety are so important, especially in environments like baptistries, swimming pools, and hot tubs. Grounding plays a critical role in electrical safety. It provides a low-resistance path for fault current to return to the source, tripping a circuit breaker or fuse and cutting off power to the circuit. This prevents dangerous voltage from building up on equipment or surfaces that people might touch. In the context of a baptistry, all metal parts of the heater, as well as any metal piping or other conductive elements in contact with the water, should be bonded together and connected to the grounding system. This ensures that if a fault occurs, the current will safely flow to ground, minimizing the risk of electric shock. A GFCI is a fast-acting circuit breaker that detects even small amounts of current leakage to ground. If it detects a difference as little as 5 milliamps, it will trip the circuit and shut off power in a fraction of a second. This is much faster than a standard circuit breaker, which is designed to protect against overloads and short circuits, but not necessarily against small ground faults. GFCIs are particularly effective in preventing electrocution because they can detect current leakage before it reaches a lethal level. They are required by code in many locations, including bathrooms, kitchens, and outdoor areas where electrical equipment is likely to come into contact with water. In addition to grounding and GFCI protection, regular electrical inspections are essential to ensure that electrical systems are safe and up to code. A qualified electrician can identify potential hazards, such as damaged wiring, loose connections, or overloaded circuits. They can also test the effectiveness of grounding systems and GFCIs to ensure that they are functioning properly. Furthermore, only trained and qualified electricians should install and maintain electrical equipment in or near water. They have the knowledge and experience to ensure that the installation is safe and compliant with all applicable codes and standards. Using non-qualified individuals for electrical work can create serious safety hazards. Some additional safety measures to consider include using double insulated electrical equipment, which provides an extra layer of protection against electric shock, keeping electrical appliances away from water, and never touching electrical equipment with wet hands. Education is also key. People should be aware of the risks of electricity and water and know how to respond in an emergency. In the event of an electrical accident, it is important to immediately shut off the power at the breaker box if it is safe to do so. Call emergency services and provide them with as much information as possible. Do not touch the person who has been electrocuted until the power has been turned off. The investigation into the reverend's electrocution likely involved a detailed examination of the heater, the electrical wiring, and the grounding system. Investigators likely looked for evidence of damaged wiring, loose connections, improper grounding, and other code violations. They also likely tested the water in the baptistry to see if it was energized. The lawsuit against the contractor likely alleges negligence in the installation and maintenance of the heater. To prove negligence, the plaintiff would need to show that the contractor had a duty to exercise reasonable care, that the contractor breached that duty, and that the breach caused the reverend's death. It is important to note that electrical codes and standards are constantly evolving to reflect new technologies and best practices. Electricians and other professionals working in the electrical field must stay up to date on the latest codes and standards to ensure that their work is safe and compliant. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations in the United States. It provides detailed requirements for wiring, grounding, overcurrent protection, and other aspects of electrical safety. Compliance with the NEC is essential for preventing electrical accidents and protecting people from harm. The NEC Article 680 covers electrical safety requirements for swimming pools, fountains, and similar installations. It provides specific guidance on grounding, bonding, GFCI protection, and other safety measures. For example, the NEC requires that all electrical equipment within a certain distance of a swimming pool be GFCI protected. It also requires that all metal parts of the pool structure be bonded together to create a common ground. In addition to the NEC, there may be local electrical codes and regulations that apply to baptistries and other similar installations. It is important to check with the local authorities to ensure that all electrical work is compliant with all applicable codes and regulations. The information in this narration is intended for educational purposes only and should not be considered as legal or professional advice. If you have questions about electrical safety, consult with a qualified electrician or other professional. The prevention of electrical accidents requires a multifaceted approach that includes proper design, installation, maintenance, and education. By following these steps, we can create safer environments for ourselves and others. The information presented highlights the critical importance of grounding, GFCI protection, regular electrical inspections, and the use of qualified electricians in preventing electrical accidents, especially in water environments. Let's consider some specific examples of how grounding and GFCI protection can prevent electrocution in a baptistry setting. Firstly, imagine a scenario where the heating element in the baptistry heater develops a fault, causing current to leak into the water. Without proper grounding, the water itself can become energized, creating a dangerous shock hazard for anyone who comes into contact with it. However, if the heater and all metal components in the baptistry are properly grounded, the fault current will have a low resistance path back to the source. This will cause a large amount of current to flow through the grounding conductor, which will quickly trip the circuit breaker, cutting off power to the heater and preventing the water from becoming energized. Secondly, consider a situation where a person accidentally drops an electrical appliance, such as a hairdryer, into the baptistry water. Again, without GFCI protection, the water can become energized, posing a serious electrocution risk. However, if a GFCI outlet is installed, it will quickly detect the current leakage and trip the circuit, shutting off power before anyone can be harmed. The GFCI is able to detect this current leakage because it constantly monitors the current flowing to and from the appliance. If there is any difference between the two currents, it means that some current is leaking to ground, which could indicate a fault. The GFCI is designed to trip very quickly, typically within a fraction of a second, to minimize the risk of electric shock. Thirdly, the NEC also specifies requirements for bonding, which is the process of connecting all metal parts of the electrical system together to create a common ground. This helps to ensure that there are no voltage differences between different metal parts, which could create a shock hazard. Bonding is particularly important in wet environments such as baptistries, where the risk of electric shock is higher. The NEC provides detailed requirements for the size and type of bonding conductors that must be used. Fourthly, regular electrical inspections are essential for identifying potential hazards before they cause an accident. A qualified electrician can inspect the wiring, grounding system, and other electrical components to ensure that they are in good condition and functioning properly. They can also test the GFCI outlets to make sure that they are tripping correctly. During inspection, the electrician may use a variety of tools and equipment to test the electrical system. This may include a multimeter to measure voltage and current, an impedance tester to measure the resistance of the grounding system, and a GFCI tester to verify that the GFCI outlets are tripping properly. Fifthly, it is also important to ensure that all electrical work is performed by qualified electricians who are familiar with the NEC and other applicable codes and standards. Unqualified individuals may not have the knowledge and skills necessary to perform electrical work safely, which could lead to serious accidents. When hiring an electrician, it is important to check their credentials and make sure that they are licensed and insured. You can also ask for references to see if they have a good reputation. It is important to remember that electricity can be dangerous, and it is always best to err on the side of caution. If you have any concerns about the safety of your electrical system, consult with a qualified electrician. Ignoring potential hazards can have serious consequences. Another critical aspect of electrical safety is understanding the different types of circuit breakers and their functions. Standard circuit breakers are designed to protect against overloads and short circuits. An overload occurs when too much current flows through a circuit, typically due to too many appliances being plugged into the same circuit. A short circuit occurs when there is a direct connection between two wires, such as when the insulation on a wire is damaged. In either case, the circuit breaker will trip, cutting off power to the circuit and preventing damage to the wiring and appliances. However, standard circuit breakers are not designed to protect against ground faults, which are the type of fault that can cause electrocution. Ground faults occur when current leaks to ground, such as when a wire comes into contact with a metal object or when a person touches an energized wire. GFCIs are specifically designed to detect ground faults and trip quickly to prevent electrocution. Another important consideration is the proper use of extension cords. Extension cords should only be used temporarily and should never be overloaded. Overloading an extension cord can cause it to overheat, which could lead to a fire. It is also important to use the correct type of extension cord for the application. For example, outdoor extension cords are designed to be used in wet environments and are typically heavier gauge than indoor extension cords. In addition to these safety measures, it is also important to educate yourself and others about electrical safety. This includes teaching children about the dangers of electricity and how to avoid electrical hazards. It also includes knowing how to respond in an emergency, such as when someone is being electrocuted. The first step in responding to an electrical emergency is to immediately shut off the power at the breaker box. If it is not safe to approach the breaker box, call emergency services and wait for them to arrive. Do not touch the person who is being electrocuted until the power has been turned off. Once the power is off, you can administer first aid if you are trained to do so. This may include CPR or other life-saving measures. It is also important to remember that water is a conductor of electricity, so never use water to put out an electrical fire. Instead, use a fire extinguisher that is rated for electrical fires. Electrical safety is a shared responsibility. By taking the necessary precautions and educating ourselves and others, we can prevent electrical accidents and save lives. Let's delve deeper into the technical aspects of grounding and bonding, two essential components of electrical safety. Grounding, in its simplest form, is the intentional connection of a circuit or equipment to the earth. This connection provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly interrupt the circuit. There are two primary types of grounding systems: equipment grounding and system grounding. Equipment grounding ensures that all non-current carrying metal parts of an electrical system, such as enclosures, conduits, and motor frames, are connected to ground. This prevents these parts from becoming energized in the event of a fault. System grounding, on the other hand, involves grounding one of the current carrying conductors of the electrical system, typically the neutral conductor in a residential or commercial building. This helps to stabilize the voltage of the system and provides a reference point for fault current to flow. Bonding is the process of connecting all metal parts of an electrical system together to create a common electrical potential. This includes metal conduits, enclosures, piping, and even structural steel. Bonding helps to minimize voltage differences between different metal parts, which can reduce the risk of electric shock. The NEC provides detailed requirements for grounding and bonding, including the size and type of conductors that must be used, as well as the methods for making connections. It is important to follow these requirements carefully to ensure that the electrical system is safe. The size of the grounding conductor is determined by the size of the overcurrent protection device protecting the circuit. The NEC Table 250.122 provides the minimum size of equipment grounding conductors for various circuit sizes. For example, a 20 amp circuit requires a 12 AWG copper grounding conductor. The grounding conductor must be connected to the grounding electrode system, which consists of one or more grounding electrodes such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must be properly installed and maintained to ensure that it provides a low impedance path to ground. The NEC Section 250.50 provides the requirements for grounding electrode systems. Bonding conductors must be sized according to the size of the circuit conductors. The NEC Table 250.102 provides the minimum size of bonding jumpers and bonding conductors for various circuit sizes. Bonding jumpers are used to connect different metal parts of the electrical system together, such as metal conduits and enclosures. Bonding conductors are used to connect the grounding electrode system to the service equipment. In addition to the NEC requirements, there may be local codes and regulations that apply to grounding and bonding. It is important to check with the local authorities to ensure that all electrical work is compliant with all applicable codes and regulations. Let's consider some examples of how grounding and bonding are applied in a typical residential electrical system. The service panel, which is the main electrical panel in the house, is grounded to the grounding electrode system. This provides a low impedance path for fault current to flow back to the utility transformer. All branch circuits in the house are equipped with a grounding conductor, which is typically a green or bare copper wire. This grounding conductor is connected to the grounding terminal in the receptacle or device box. All metal parts of the electrical system, such as metal conduits, enclosures, and appliance frames, are bonded together. This helps to ensure that there are no voltage differences between different metal parts. Ground fault circuit interrupters or GFCIs and arc fault circuit interrupters or SIs are both critical safety devices in modern electrical systems, but they serve different purposes and protect against different types of electrical hazards. As previously discussed, a GFCI is designed to protect against electric shock by detecting ground faults. A ground fault occurs when current leaks to ground, such as when a person touches an energized wire or when a wire comes into contact with a metal object. The GFCI constantly monitors the current flowing to and from an appliance or device. If it detects a difference of as little as 5 milliamps, it will trip the circuit and shut off power in a fraction of a second. This is much faster than a standard circuit breaker, which is designed to protect against overloads and short circuits, but not necessarily against small ground faults. SIs, on the other hand, are designed to protect against electrical fires caused by arc faults. An arc fault is an unintentional electrical discharge between two or more conductors. Arc faults can occur when wiring is damaged, loose, or corroded. It can also occur in appliances with worn or damaged cords. Arc faults generate heat, which can ignite nearby combustible materials and start a fire. SIs detect arc faults by monitoring the characteristics of the electrical current. They are designed to distinguish between normal arcing, such as that which occurs when a switch is turned on, and dangerous arcing, such as that which occurs when wiring is damaged. When an SI detects a dangerous arc fault, it will trip the circuit and shut off power to prevent a fire. SIs are typically installed in bedrooms, living rooms, and other areas where there is a high risk of electrical fires. The NEC requires SIs in many locations, including all 120-volt, single-phase, 15 and 20 amp branch circuit supplying outlets or devices installed in dwelling units. GFCIs and SIs provide complementary protection against electrical hazards. GFCIs protect against electric shock, while SIs protect against electrical fires. Both devices are essential for ensuring electrical safety in homes and businesses. Regular testing of GFCIs and FCIs is important to ensure that they are functioning properly. GFCIs can be tested by pressing the test button on the device. If the GFCI is working properly, it will trip and shut off power to the circuit. FCIs can be tested by using a special FCI tester. The FCI tester simulates an arc fault to verify that the FCI is tripping correctly. If a GFCI or FCI fails to trip when tested, it should be replaced immediately. Electrical safety is a critical aspect of home and workplace safety. Grounding, bonding, GFCIs, and FCIs are all important components of a safe electrical system. By understanding how these devices work and by following the NEC and other applicable codes and standards, we can prevent electrical accidents and save lives.